Okay, welcome to Note Set 14. Not MATLAB, but regular linear algebra stuff. And we're going to start talking about a space of vectors, or a better way to say that actually would be vector space. We'll see shortly what that means. This is in section 3.1 of our textbook. So vector spaces, and so here is a quote from the author of the textbook we've been using in lecture 5 of his online MIT course, and I completely agree with this. He says it's the beginning of real linear algebra. So up until now we've really been focusing on how to solve systems of linear equations, and so those kinds of ideas were well known for how to do that for a long time before linear algebra really became formalized. And so what we're about to start talking about here is something that really goes to the heart of solving those linear equations, but also shows how it's connected to a whole bunch of other stuff. And these ideas of vector spaces pervade all sorts of other areas of math, science, engineering, and so forth. So much about the real world ends up being described in terms of vector spaces. And really, we won't really get into the details of this here, but this is something that mathematicians kind of abstracted out of things that were coming out of the physics world. So physicists were talking about forces, describing them in terms of vectors, and things like that, and they were talking about additions of forces, adding two vectors together to get another vector that was describing the force, or the velocity vectors, things like that. And mathematicians, what they often do is just look at what's going on in the physical world, and leave that to the scientists and the engineers, but try to understand what's at the heart of it. How far can we strip this down, or how far can we stretch it into things that behave the same way but don't look at all like what we were originally talking about? And so that's what the mathematicians did. And we're not going to really dwell on that, but we'll mention it in a couple spots here and there. So basically what we're interested in looking at is we've got a bunch of vectors. Say we've got one or two or more vectors. We can add them together, and we can multiply any vector by a scalar. And so the idea is we'd like to have a collection of vectors that when we do these things to them, we just get another vector in that collection. And that provides a very powerful structure or fabric within which to work. And some very powerful ideas come out of this viewpoint that help solve the systems of linear equations as well as do a bunch of other stuff. So every time you fly on an airplane, there's stuff going on in there that's keeping that airplane flying straight and level, and not going crazy, and knowing where it is and where it's going. All that stuff is actually highly based upon the concepts of vector space. So here's some examples. First one you should be really familiar with. So R2, remember we're using that symbol, and some books use other symbols than this curly R. This is the one that we're using in the notes here. So R2 consists of all two-dimensional real valued vectors. So here's just a couple of them, 3, 0, 0, 0. Remember, this is just our lazy way of writing column vectors. So think about that entire plane, that entire so-called XY plane, if we think about one of these elements being X and the other one Y, although we've been using like X1 and X2. So think about that plane and the abstract concept of that plane. It goes on forever. It's not like, Kansas, which is flat and seems like it goes on forever. But this plane really, really goes on forever. And therefore, if we were to take any two vectors in R2, and add them together, we'll get another vector that lies in R2. Because the two vectors started off in the plane, adding them together cannot get them out of that plane. Same kind of thing. Take any vector in R2, multiply it by another number, positive, negative, integer, non-integer, rational, irrational, doesn't matter. As long as it's real, multiply that vector by that number and you'll get another vector that's in the plane. Can't get out of the plane. That's the idea that we're after here. But what if we talk about a vector that we say is 3, 2, 0? Well, we could think about it really being in R3. But if we limited ourselves to only vectors that had these first two elements non-zero and this third element always 0, well, it's really technically in R3. But we could think of it as those vectors can never get out of that two-dimensional plane that they lie in if we add or subtract them or we multiply them by a number. So in some sense, there's an R2 plane embedded inside the R3 space. And so that will give rise to the concept of a subspace. So if we limited ourselves to vectors that in R3 that only had a 0 there, that would be a set of vectors that would be a subspace of R3 because they lie on a plane. But what if we tilted that plane so that it's not perpendicular to the third axis? We could tilt it. And now if we limited ourselves to vectors that lay only in that plane, that even though it's tilted, they'll have, all three elements will potentially be non-zero. But because we're limiting ourselves to things in a plane, it's still like a subspace of R3. It's not all R3, but it would still satisfy this idea of adding them together stays in that plane, multiplying by a scalar stays in that plane. So these are the ideas we're after. So let's nail some of this down. So we've got arithmetic properties. So we've got vector addition. We know how to do that. We've got scalar multiplication. We know how to do that. So suppose we've got x, y, and z are vectors. I'm not going to tell you whether they're in R3, R2, whatever. They're just arbitrary vectors. And we say of the same dimension, so they have the same number of elements in them. And let alpha and beta be two arbitrary scalars. Then we know that the following properties have to hold based upon how we defined vector addition and scalar multiplication. So it doesn't matter which way that I add x plus y or y plus x. Okay, we can see that. It doesn't matter if I think about multiplying from the front or multiplying from the back, or from the left or from the right, with scalar multiplication. It has the same property. So both of those arithmetic operations are commutative. We also note that these properties have associativity. I can do x and y first, then z, or I can do x and z first and then y. And same kind of thing here. I can do beta times x, then multiply that by alpha, or I can do alpha, beta together first and then multiply that by x. Get the same thing. So that's the associativity property. We have the distributive property that holds for how we define vector addition and scalar multiplication. So we can distribute this alpha through, or we can distribute the x through, either way. And then there is also a scalar unity. So there is a number, and in our case it's 1. There's a number 1 that when we multiply it by a vector gives us back the same vector. Okay? And there has to be a scalar 0. So that when we multiply any vector times that 0, we get the 0 vector. And so these things seem pretty obvious, but as I said, mathematicians kind of like to abstract things, and so they started looking at these things which hold for the vectors that physicists were starting to use, and they said, well, why couldn't we find other things that behave like those vectors, but are not necessarily just stacks of numbers but they would still behave this way. So don't worry too much about whether that makes no sense. I'm just trying to put a little perspective here. As far as the course and as far as an engineer goes, you only need to know how to sling these real vectors. Okay. So let's define what we mean by a vector space. A vector space is a set of vectors, so a set V of n-dimensional vectors, and we haven't really defined what we mean by n-dimensional yet, but for our purposes it just means that a stack of n numbers into a column. But again, the mathematicians have a more abstract way of defining all that. And there has to be some corresponding set of scalars. So for our rule for this course is that if we're talking about stacks of numbers, if those numbers are all real numbers, are limited to be real numbers, then our scalars are limited to be real numbers. If the vectors are allowed to have complex numbers in them, then our scalars will be the set of complex numbers, which includes the real numbers as a subset, by the way. So we define a vector space as a set of vectors that all are the same size as far as dimension. And this is what's special. It's not just any old set V. It's a set that it's closed under vector addition. So I take any two vectors in V, add them together, and I must get another vector in V. And that must hold for every possible pair. So if you think carefully about this, the set V here just can't be a handful of vectors in general. Think about that plane R2. It's got all the possible two-dimensional vectors in it. So it's huge. It's boundless. The other thing we need is closed under scalar multiplication. So any vector in V, we multiply it by an appropriate scalar limited to reals if our vectors are limited to reals, and we end up with another vector in the set. So remember, scalar multiplication stretches and shrinks and possibly flips the vector. So clearly, to be a vector space, it can't just be a finite collection of vectors. There has to be infinitely many of them in there. But that alone isn't enough, as we'll see later on. So addition of vectors gives another vector in the set. Scalar multiplication gives another vector in the set. That's what we mean by closed under these operations. And if we combine these two things together, we can say this all in one combination or one statement. We can say that a vector space is a set of vectors such that any linear combination of vectors in the space results in another vector in the space. So it's closed under linear combination. And notice that linear combination just is, includes these two things working together. So if V1, V2, and V3 are all vectors in a given vector space, then this linear combination, alpha 1 V1, alpha 2 V2, alpha 3 V3 for any alpha 1, alpha 2, and alpha 3, and we can write this more compactly this way, will also be in the vector space. And we don't have to limit ourselves to just three of these. Could be any number of them. So I just want to touch briefly, this is what the mathematicians call the axioms of vector space. So really they've abstracted this idea and say anything that behaves with the following, so satisfies the above, closed under linear combinations, also satisfies the following axioms. So really they do it the other way around. They pose these axioms and say anything that satisfies these axioms will be a vector space. But here we're just writing them down as not so much axioms that establish something and more as things that come out of. So we've got our vector space, and then these are some properties that we get. So we've already talked about commutativity, associativity, distributivity, and the unity and zero scalar. There has to be an existence of an additive identity in the vector space. So in our vector spaces that we've been talking about, additive identity means a vector that when I add it to any vector doesn't change it. So that's the zero vector. It's the vector of all zeros. So in other words, any vector space V must have something that acts like a zero vector. So for us, it's just a stack of zeros. But for the mathematicians, it could be something else that's weird and wacky, but behaves like the zero vector. Yep, those mathematicians are always doing the weird and wacky things, but it's often really, really cool what they come up with. There also has to be a negative vector. So for every vector in V, there has to be something that acts like it's negative. And what we really mean by that is there's another vector that when we add it to V gives us what we defined as our zero vector. That's the concept of existence of a negative vector. So we can see that our concept, a stack of numbers, satisfy with how we defined vector addition, how we defined scalar multiplication, satisfies all of these things. And embeds in R2 or R3 or R4 or even all the way, R1000, R1 million, it doesn't matter. Any one of those vector spaces has some sort of arithmetic structure built into it that links the individual vectors together in their behavior. And so that's the concept of a vector space. So for us, the space we're going to be dealing with arbitrarily are n. So, for our examples, we'll be keeping n kind of small so we can see things. So we'll be looking at R2, R3, maybe R1, which is just the real numbers, which forms a vector space, by the way. But there's no reason, like I just said, that we can't let n be some, very large number. We could be talking about 1,000-dimensional space or a 1,000,000-dimensional space. Everything will work exactly the same way. We're going to limit ourselves to the components of our vectors will be real numbers. Sometimes in engineering, we do need to allow our vectors to be complex valued, in which case, instead of saying Rn, we would say Cn. And so here's an example of a vector that's in C2. So there's a complex number, 1 plus I, and here's a complex number, 1 minus I. This is using I that the physicists and mathematicians use. Electrical engineers tend to use J, but same idea. But we're going to limit ourselves primarily to talking about real valued vectors. And so even though, here's the cool thing about linear algebra. There's nothing special here about the 5-dimensional space. It can be anything. 1,000. It can be 1,000,000, whatever. We learn the rules for the arbitrary n dimensional space, and everything will work regardless of what the size is. But the statement here is that for 5-dimensional space, to describe a vector in that, we just need 5 numbers. But what's really important is how those 5 numbers will interact with another set of 5 numbers to create yet another set of 5 numbers, and it'll all reside in some 5-dimensional vector space. Now here we'll just take a moment to just hop over into the abstract vector world to see what mathematicians say about these. So here's some curious things that are vector spaces other than the vector spaces that we'll be concerned with, which are the Rn spaces, which the vectors are just stacks of n real numbers. So here's one. Wait a minute, what are you saying? That matrices are vectors? Yes. I know it seems weird. It sounds like we're saying, some sort of oxymoron, out of Orwell's 1984. Love is hate, peace is war, vectors are matrices are vectors. But we can do this because they behave like that. So if you talk about 2 by 2 matrices and you define how we defined addition, you will find that they satisfy all of those conditions that are needed to make it a vector space. Now this one's interesting, and this one actually is used in some of the higher level electrical and computer engineering classes. We do think about the vector space of all real valued functions. So if we have one function and we have another function and we add them together, we get another real valued function. And in fact, it satisfies all of the rules that we just saw. And these symbols out here that are being used are somewhat arbitrary. So this is what the book uses as symbols for this, but there aren't necessarily any hard and fast rules that say F has to be this used to describe this space. Now the interesting thing about this is that that space is actually infinite dimensional. Now if you think about it, that kind of makes sense. Think about a function. Let's limit ourselves to functions, say, between 0 and 1. So we can look at all the functions that are defined on this space. I didn't quite get to 0 there. All these different functions. These are all different functions on 0, 1. Well, think about a vector. We can take a vector that we've been talking about and think about 1, 2, 3, and let's count the 0. We can put points here. Whoops, that didn't work so well. We can put points here. So there's 4 points on 0 to 3. So this is 0, 1, 2, and 3. So we're defining a function only on the integers. So that's 4 points. That's 4-dimensional. That if we took these values that these points are at and put them into a vector, that gives me a 4-dimensional vector. Well, up here, how many points do we have? How many points are there on this curve? Infinitely many. In fact, what mathematicians call uncountably infinite many. So that's why, in some sense, we can say that this is an infinite dimensional space. But again, don't freak out over this. This is just, we're just taking a glance, over into the abstract world of mathematicians. Well, here's an interesting one. Let me clear some of this stuff off here so we can see a little bit better. Remember I said that vector spaces have to have lots of vectors in them, but if you go back and you listen, I said in general vector spaces have to have lots of vectors in them. But here's one that has only the 0 vector. So that one actually consists of, and it doesn't even really matter how many zeros you stack in that case. So you can just think of an abstract 0 vector. Now, add the 0 vector to itself, you get the 0 vector. Multiply by a scalar, you get the 0 vector. So it's kind of a default satisfaction of all those conditions. So it's not terribly interesting, but it is kind of odd. So you go, okay, yeah, I guess I got to let that in. And the dimension of this space, well, it's 0-dimensional. Now you might say, well, wait, I thought you just said I could stack as many zeros as I wanted. There's actually a more general way to define the idea of dimension, and it has to do with how many vectors do we need as kind of building blocks to make sure that we can build all vectors. So later when we get into those ideas, it may make more sense as to why this vector space is 0-dimensional. So in each one of these cases, we can show that it's closed under addition, it's closed under multiplication by a scalar, so when we do those things, if we started with things in M, they stay in M. If we start with things in F, they stay in F. If we start with the one thing in Z, it stays in Z. So it's sort of like that saying, things in Las Vegas things that happen in Las Vegas stay in Las Vegas. Las Vegas apparently is a vector space. Things that happen in a vector space stay in the vector space. So here's a question. Is this a vector space? So, I only show it as a a rectangle out so far, but we're really saying this is 1/4 of R2. So this goes on and infinitely far in that direction and infinitely far in that direction, but it's bounded by these two axes. So is that a vector space? I'll let you pause the video here and think about that. Hopefully you haven't looked ahead on your notes, but pause it, think about it, come back, and I'll answer it. Okay, so hopefully you had a chance to think about this, and hopefully you didn't see the answer before you had a chance to think about it. Well, it's not closed under multiplication. It is closed under addition, interestingly enough. You take any vector, so think about a vector here and a vector here. Since they must lie in the quarter plane, you add them together, you'll get something, using the parallelogram rule that's out there. So that by addition, there's no way we can get outside of this quarter plane. But what about multiplication? Remember, we can multiply by negative scalars, so it's got to be able to come back over here. So in order to be closed under multiplication, we would also need to include all of these here. So this quarter of R2 is not closed under scalar multiplication and therefore is not a vector space. Now let's talk about definition of a subspace. So given a vector space V, subset of vectors in V that itself is closed under vector addition and scalar multiplication using the same set of scalars. Okay, so that's important. That requirement is what makes it impossible to have, say, R2 be a subset of C2. So here's some examples. R2 is a subspace of R3. We talked about that when we talked about vectors that had the form that were like this. So, we have some number here, and we have 0 here. So those would be really limited to a subspace R2, and if we add them together, they stay in R2. If we multiply by a scalar, they stay in R2. So technically this is in R3, but it behaves like it's in R2. And likewise, as I alluded to earlier, any plane in R3 that passes through the origin, regardless of how it's tipped. So R2 is actually a plane that passes through the origin in R3, but it's not tipped. It's orthogonal to the third dimension, and that's why in that case all the third elements are always 0. But any plane that passes through the origin, if you is going to be closed under addition, closed under scalar multiplication, so closed under linear combinations. Any line passing through the origin in R2 is a subspace of R2. Likewise, any line passing through the origin in Rn is going to be a subspace of Rn. And then here's why R2 is not a subspace of C2. C2 is our originating space. Yes, R2 is enclosed in C2, so anything that's in R2 is also in C2, but it has to be closed under the same scalars. So as soon as I take something that's in R2 and multiply it by a complex scalar, it's back in C2. So it's not closed, so it's not a subspace. So this is just reiterating our definition here. Subspace of a vector space is just a set of vectors, and it must include the 0. So we can't just not include 0. That's a requirement to be a subspace. And we're just saying that it has to also satisfy closed under addition and closed under that. So here's some two subspaces in R3. So the three axes are defining our three-dimensional space, and then we've got a plane that is perpendicular to the third axis, so that's the R2 plane. Although we could show it as being tilted in any way as long as it goes through the origin. And then we've got a line that's kind of tilted here, but also goes through the origin here. And so those are each subspaces. So you add any two things in P and you'll get something else in P. You add any two vectors that lie on that line L and you'll get another vector that lies on that line L. So here are some questions. If you want to pause and think about it before you come back, and I'll answer it. The union of P and L, that's what that symbol U means. The upside down U means the intersection. So are those subspaces? So pause and come back and we'll talk about it. All right, hopefully you have paused. So every subspace must contain the 0 vector. And so certainly the union of this contains the 0 vector. So that certainly is okay. But the union of these two, so that would mean I've got all the vectors in this plane plus all the vectors on this line. But as soon as I try to add them together, so let me say I take something here and something here, where is that going to lie? It's going to lie here off from the union of those. So this is not a subspace because it's not closed under addition. What about P intersect L? What actually is that? So it has to be all the elements that are in both. Well, we've got the plane, we've got the line sticking through it. Let me try to clear this ink off here. The only point that's in both of those is right there, 0. Ha! Well, so the intersection of them is a vector space. It's that 0-dimensional vector that is, or 0-dimensional vector space that is just the 0 vector. Now notice that when we talk about, we had our 3-dimensional subspace, or our 3-dimensional space needed 3 axes. It was, what we think about as 3-dimensional space. A plane ended up being a 2-dimensional space. And remember, this blue region here must really extend out forever. And then we've got the line, so it really should also have an arrow going in that direction as well. That's a 1-dimensional vector space. I only need one vector to define that. 2 vectors will allow me to define a plane, and 3 vectors will allow me to define a 3-dimensional space. And so what about the dimension of this? P intersect L. Remember, that's just this one point. How many vectors do I need to define a single point that happens to be at 0? Well, I need just one vector, the 0 vector. So that's a 0-dimensional subspace. So you'll need to make this connection between dimension of subspaces and what their geometrical shape is. So a 0-dimensional vector space is a point at the origin. Any 1-dimensional vector space, at least in the context that we're thinking here, will be some line through the origin, and we can picture that in a 3-dimensional space, but there's no reason why we can't think about it in higher dimensions, 4, 5, 6, 1,000, 1,000,000, whatever. So in those higher dimensional spaces, we're actually thinking about what we would call a hyperline. And then here we're seeing a plane as a 2-dimensional space, a 2-dimensional subspace. In a higher dimensional space, we could refer to those as hyperplanes. And really we could extend that idea when we have, say, a 5-dimensional space and we look at a 3-dimensional subspace of that. We'll call that 3-dimensional subspace a 3-dimensional hyperplane. So the terminology gets kind of weird, but you kind of need to stretch your brain a little bit to wrap it around these things. Okay, let's revisit one of the examples we just saw. We looked at the 1/4 plane, which was this stuff up here, and we showed that was not a subspace. We said that it satisfied addition, but it didn't satisfy the multiplication. And we argued that it didn't satisfy multiplication because it was missing those. So suppose we add those in. So now we've got the two quarter planes. So we've got everything up in this first quadrant, everything down in the third quadrant. Is that a subspace of R2? Remember, it's got to satisfy everything. Well, let's check to see. In general, we would check whether it's closed under addition and multiplication, and then we could also check to see if it satisfies all those axioms. Now, we already said we needed this part down here to satisfy the multiplication, so that certainly works. But now we have to recheck addition. So notice that if I had this one and, well, that wasn't a very good drawing. Let me try to clear this off here and do this again. Let's say I have this one that lies right on the axis and this one that lies right on the axis, and I add them together. They're going to be out here. So it's not actually closed under addition. So we fixed the closed under multiplication part, but we broke the closed under addition part. So this is not a subspace of R2, and neither is the quarter plane. So here's another example. So we've got the space M of all 2 by 2 matrices. We're not really going to spend much time with these abstract vector spaces, but this is just kind of interesting to talk about as an aside. So here are two allowable subspaces of that, all upper triangular matrices. So notice that if I take two of these things and add them together, I'm never going to get anything here that's not 0. So they're closed under addition. And what about if I multiply by some scalar alpha? Again, I'm never going to get anything here other than 0. So upper triangular 2 by 2s are a subspace of all 2 by 2 matrices. Interesting. What about diagonal matrices? Yep, same thing. If I add them together, I'll still have diagonal. If I multiply by any scalar, I'll still have a diagonal. So yes, not only is D a subspace of 2 by 2 matrices, but it's a subspace of upper triangular. So we can have a subspace of a space and a subspace of a subspace. And there's really no end to that to some degree. And so now that we've got this idea of a vector space under our brains, so to speak, let's see where we're mostly going to apply this idea. There's lots of other places to apply this, but for us, studying the solution of AX equal to B, which is kind of the main focus of this course, the idea of vector space creeps in a very important way. So let's take a look at how we're going to do that. So here we've got a matrix A. Now, I know you might look at that and say, wait a minute, that's not square. I thought we were talking about square matrices for A here. And to a large extent we are, because that gives us at least a chance of solving this in the way that you've kind of been taught. You may have been taught that you need as many equations as you have unknowns, and that's what leads to a square matrix there. But there are times when we need to solve this for a rectangular matrix, and in this case we have more equations than we have unknowns. And so this is what would be known as an overdetermined system of equations, and those show up. And sometimes we have underdetermined systems of equations, and those do show up sometimes too. But to really understand how all of this stuff works, we kind of need to solve this or understand the mechanism of how this all works for all the different cases of A, whether they be square, rectangular, and tall, like this one is, more rows than columns, or rectangular and short, like that one would be, maybe 2 rows and maybe 4 columns or something like that. But let's just look at this example here. Let me clear the space or the ink off here. So here's an example, and we can immediately see for this example, these two vectors don't lie on the same line. That's pretty easy to see. So that's interesting. And what we're going to look at is we're going to define this thing called the column space. And I've just put this example up here so that we can point to it and think about it. So the column space of a matrix, we'll denote it by C of A. So that represents all the possible linear combinations of these two vectors for this particular A. So we would take the first column times some arbitrary alpha plus some arbitrary beta times the second column, and let alpha and beta take all possible values, and all the vectors that get generated by that will make up a space. And it will be a subspace, in this case, of R3. And we want to know, like, how big is this space? So when we were talking about this picture back here, let me go back just a little bit. When we were talking about this picture here, we were in R3, but we talked about this subspace, a plane. So a plane kind of fits inside R3, and so in some sense it's smaller than R3. And certainly the line L is in some sense smaller than R3. And the intersection of P and L, the zero vector space, is much, much smaller than R3 in some sense. And so we need to have some way of measuring how big is this space, and we'll drive towards that. So in other words, does it fill all of R3, or is it some line or some plane? So remember, subspaces of R3 are going to be things like lines and planes. And so if we can figure out what the column space looks like, then we'll be able to figure out what's in that column space. And remember, if we're trying to solve AX equal to B, well, B is formed as a linear combination of the columns of A. That's how we interpreted this multiplication way back a number of note sets ago when we looked at, 5 or 6 different ways to visualize matrix times vector. And one of them was it forms a linear combination of the columns. So clearly, if B cannot be formed by linear combination of the columns of A, there is no X that will allow us to form B that way. But the column space is all linear combinations of the columns. So what this says is that to answer this question, does AX equal B have a solution for every B? The answer is no. Only those B that actually lie in the column space. The answer to this question is only those B's that lie in the column space. So the column space for this case is 1, 2, 3 forms one vector, 1, 1, 1 forms another vector. It turns out to be a plane in R3. So if I pick a B that lies in that plane, then and only then can I find a solution to this. If I pick some other B vector, then there's no X values that will allow me to combine those two columns to get that B. So this is extremely important. So which B's are allowed to be allowed to give rise to a solution? Well, I just told you it has to be in the column space. But one of the easiest ones to see is if all of these were 0, well, then I certainly have at least one solution. Just set those to 0. So there is a solution. There will always be a solution when the B vector is 0. And that'll be a special case that we'll look at soon. What about 1, 2, 3? Well, that certainly is in the column space because it's one of the columns. So yeah, it will have a solution for that. And what would the solution be? Well, the solution would be 1 and 0. So the 1 will select the first column, the 0 will annihilate that, and we can form 1, 2, 3 as the B vector from just the first column of A. What about linear combinations of 1, 2, 3, and 1, 1, 1? Yeah, that's actually the whole picture right there. Anytime we have B that lies in the space that's the linear combination of the columns, so in other words, the column space, then we have an answer. So in other words, we can solve AX equal to B only, where'd my pointer go? There we go. Only when B is in the column space of A. And so for this example, it was a plane. The plane that holds these two columns, so those two vectors. So remember, take any two vectors that aren't on the same line and they define a plane. So grab a couple pencils, put their erasers together, anchor it down on the table, and imagine drawing, laying a piece of paper so that it's flat against those two pencils. That's the plane defined by those two vectors. Any two non-collinear vectors will define a plane. So if I've got two vectors that are not on the same line, so remember that means they're linearly independent. So as soon as I have two vectors here that are linearly independent, which they are, then I'm going to get a plane. So the more you think through this, use pencils, chopsticks, whatever to visualize this, the better you'll be at all of this. So here's our definition in a big yellow box with a red border. So just defining what the column space is. These linear combinations are all the possible vectors that can be formed for some choice of x. And that is the column space C of A. So if it's the set of all vectors that can be formed this way, if we put something B over here that's not in the column space, then there is no x that will allow us to form it. So this is a really central idea to this entire course because it tells us when we can solve this set of equations. So there it is again. It's important, so I'm reiterating it. The right side B has to be in the column space. Otherwise, no solution. And there it is again. So I think you should be getting the idea that this is important. System x equal to B is solvable if and only if B is in the column space. So let's take a look at some column spaces here. So here's three matrices. So I'll ask you to pause and think about this, and then you can come back. Okay, so let's look at the first one. The first one is the identity matrix, 2 by 2 identity matrix. And so if we look at linear combinations of those, let's take A times the first column plus B times the second column. That gives us all vectors that can be of the form A, B. So that's actually all two-dimensional space. So the column space for this one is all of R2. And that kind of makes sense. What are the solutions to Ix equal to B? I can put any B here, and the solution is x is equal to b. So that makes complete sense. What about this one? What can we say about that? Look carefully at it. Look at the relationship between the two columns. The first column is 1, 2, and the second column is 2, 4. How can I get the second column from the first one? Well, I could take the first column and multiply it by 2 to get the second column. So they actually lie on a line. So the column space of this matrix is a line, and so if I draw my two-dimensional space here, so I've got 1, 2, there's my point. So there's that first vector. The second one is out here at 2, 4, also on that line. So any B on this line would lie in the column space. So for that A, if I'm putting it into this system, unless this B is selected so that it lies on that line, there will be no solution. What about this last one? So, well, let's back up. So we saw one where the choice of B is completely unconstrained. We saw another one where the choice of B is fairly constrained. What about this last one? Well, certainly I can create the second column from the first by just multiplying by 2. But can I create the third column from the first two? No. There's no way I can create anything from the first two through linear combinations other than vectors that have zeros here. So clearly that second or that third column is linearly independent from the first two. The second column is linearly dependent on the first one. So actually the column space of this B matrix will be all of R2 because I can think about it this way. So here's my R2. We don't even really need to consider this one because I can always make that one from the first one. So here's 0, 1, and then here's 3, 4. So I've got this vector and I've got this vector. And by adding those two, any linear combination of those, I can actually get anything in R2. So the column space of B, all of R2. So in that case, you give me any B. If I now put this up here, instead of A here, I put this matrix B, I can put any B here and there will be a solution. Now the next question that we should ask is it a unique solution? Well, we'll answer that much, much later. We've got some machinery that we need to learn first. But think about it. I gave it away already. I said that, let me clear this off. I said that these two vectors are kind of redundant. Anytime I need this one, I could get it from this one, or vice versa. If I needed this one, I could get it from this one. So in some sense, I can create a bunch of solutions that use the first column, and I could also have totally equivalent solutions that would just use the second column to create the first column and substitute that into that solution. So I could have multiple solutions. So that's interesting. So we're poking at this. We're saying we're nailing down now when is there a solution, and later we'll be nailing down, okay, when there is a solution, is it unique or is there multiple solutions? Important concepts that we'll be talking about. So I want to introduce a term called the span because it's a nice term to be able to just throw out there. We've already kind of been running around this concept. We just haven't put a name on it yet, and so it'll be nice. This comes up over and over again, so it'll be nice to just have a name for it. So suppose we've got some, let me clear that ink off if I can. There we go. Suppose I've got some vector space V, and I've got some collection, finite collection, 1, 2, all the way out to M. I've got some finite set of vectors that are in V. Doesn't matter where they point, doesn't matter how many of them there are as long as they're finite. So we know that S by itself is not a vector space because we already argued that with the exception of the zero space, every other vector space kind of has infinitely many vectors in it due to the, it has to be scalable by scalar multiplication. So certainly S is not a subspace of V, and in this case, I've made sure of that because I've said I just have a finite number of them. Let SS be the set of all possible linear combinations, and this SS is not a defined symbol that we'll be using over and over. I'm just using it here. So let SS be the set of all possible linear combinations of these elements in S. So you can see the SS is like span of S, something like that is why I called it that. So in other words, each element of SS has this form. So now, even when S is not a subspace, this will actually form a subspace of V, and could possibly even form all of V, but it certainly will form a subspace of V. And so what we say is that this subspace is the span of this set S. I think I failed to include that in the notes here. I better go back and change that. I didn't I didn't hit the nail here to say what the name span means. So I'll fix that. But basically, we're saying that SS is the span of S. So the span of some set of vectors will form a subspace. So we can use this terminology instead of having to say the column space is the set of all vectors that are the linear combinations of the columns of A. We can just simply say column space is the span of the columns of A. So it's just a term that we'll use to shorten up what we have to say. There's really no new idea here. And I promise I'll fix this slide before I post it. So the concept of the term span is just a new way to talk about the column space, but it doesn't have to be the column space. The set of vectors that I'm talking about don't have to come from the columns of some matrix A. And that leads us to the idea of the dimension of a vector space. So at the beginning, I said, think about, for us, dimension is the number of elements in the vectors, but we started to see that started to fail us a little bit when we started looking at the set of all vectors that had, say, A, B, and 0. So we said if we looked at that set for all possible A and B, that did form a vector space, and we talked about it being a subspace of R3, and we talked about it really being a plane in R3, and in fact we said it was really like R2, the restricting it to that two-dimensional plane that looked like R2, and we said, oh, two-dimensional plane. So even though this has 3 elements in it, there's only 2 of them that are doing anything. The third one is constrained. So here's a better way to define the concept of dimension without ever even having to look at how many elements are there in there. So if we've got some vector space V, and it may be a subspace of some other bigger vector space, we say that dimension of V is defined to be the smallest number of vectors needed to span V. So if we go back to our AB0, which I've already inconveniently erased, if we go back to that, how many vectors do we need to span that? Well, we could easily create that this way. Scalar A times 1, 0, 0 plus, I'm going to go down to the next line here. I wish I'd left more room. B times 0, 1, 0. Oops, not very good there. So I think it's pretty clear that from these 2 vectors, I can form any vector of that form. So that subspace is spanned by just 2 vectors. And in fact, I can't eliminate one. There's no way I can eliminate and get it down to 1 vector that would span the space defined by all vectors of this form, A, B, 0. So the dimension of that space is 2. And in fact, even if I had some more complicated thing here, A, B, C, but with some constraints on A, B, and C, that defined some plane that went through the origin, but not perpendicular to the third axis, I would still find that any plane in R3, I can span it with just two vectors. And remember when we were talking about this earlier, I said get out your pencils, get 2 pencils, and anchor their erasers together down on a tabletop, and then lay a piece of paper over those 2 pencils so that the piece of paper is touching the pencils, each pencil everywhere along its length. That's the plane that those 2 vectors define. So 2 vectors completely define a plane. So you only need 2 vectors to span a plane. So that's why we say a plane has a dimension of 2. So it's a subspace of R3 that has a dimension of 2. So this idea of smallest number of vectors needed to span something gives us the idea of dimension. So R3 has dimension 3 because we need at least 3 vectors to span it. Any plane in R3 that includes the origin is a subspace of R3, and we only need 2 vectors to span it, so it has dimension of 2. A line in R3 that includes the origin, I only need 1 vector to span that, so the line has dimension of 1, and so on and so on. So here's an exercise. I'll leave you to try this. Hopefully you haven't looked ahead in the notes. You can give it a shot, and then pause it, come back, and I'll take you through the solution here. But what we're being asked here is, given 2 different vectors, B1 and B2, we'd like to find a matrix A that will allow us to give a solution for each of these cases. So here's the solution. So we want an A such that both of these B's are in its column space. So the easiest way to do that is to just put the B1 and B2 in as the columns of A. And so then the solution for the first one, AX equal to B1, would be 1, 0, and the solution for the second system would be 0, 1. So that's it for this set of notes, and I'll see you in the next one.